My name is Elishtereva from F6S. I'm going to be hosting this session today. This second session is a part of our mini-series format titled The Future of Materials Manufacturing, Embracing Open Source Digital Solutions for SME Growth. The purpose of this sessions is very simple. We just wanted to provide you with a very easily digestible knowledge on the existing opportunities behind open source digital solutions for material manufacturing SMEs and how they can support you in your digital transformation journey, facilitate your business and operational processes along the way. What you can expect from our sessions is not only understanding the trends and challenges in material manufacturing and exploring the importance of digitalizations for SMEs, but understanding exactly how open source digital solutions can support your journey and also how easily integratable are those solutions for you. We are also going to explore what DiMAT digital solutions are and how they support this overall process, and as well different opportunities for SMEs to actually join our project through our call for early adopters, where you are going to be able to explore, test, and also provide feedback for the development of these solutions in order to make them as fit as possible for your specific needs. Regarding those webinars, we already had our first one, which was held on the 21st of November, where we provided more or less an overview on the digital trends and challenges across the material value chain for material manufacturing SMEs, where we focus on the main trends and opportunities within the field. And also we have presented the three suites developed by the DiMAT project. Now we're going to move to the three different main topics across the material value chain. And today we're going to start with material data management, operationalization, and life cycle assessment. We're going to be speaking about data management, about knowledge graphs and how they're relevant for your business process and presenting the analysis that you are undergoing, and also a life cycle assessment analysis for non-specialists, which I believe is also very interesting for different people that do not have the expertise but actually can make use out of it. On the 11th of December, we're going to continue with predicting material behavior and advancing material design, where we're going to be speaking about different digital solutions that are going to support you in cutting costs and time in material testing and also material production. And then on the 17th of September, we're going to be speaking about the digital twins and digital simulation in material manufacturing. Now we're moving to the topic of today, material data management, operationalization, and life cycle assessment. And before I give the floor to our speakers, let me present them to you. First, we have Lukas Morand, who is a researcher at Fraunhofer IWM. Then we have Konstantinos Tsitseklis, postdoctoral researcher at the National Technical University of Athens. And we have Thanasis Karagounis, who is an associate project manager and LCA expert at DRAXIS Environmental. You already know me. I'm going to be hosting today's session. This is the brief agenda for today. I have already gone through it. Main thing that is important for all of you is we have a Q&A chat box which you can see on the bottom of your screen. Whenever you have a question, please just write it in the chat box, and any of our experts is going to answer as soon as possible. In case we have time at the end of our session today, we're as well going to answer some of the questions live. Otherwise, we're going to be doing it simultaneously while the presentations is going. As many questions as you have, please share them with us. We're here to support you. And as I said in the beginning, this is the goal of our sessions, to provide you as much as information possible regarding digital solutions for material manufacturing SMEs. And this is it. Now we're moving to the first presentation, which is going to be delivered by Lukas Morand. Lukas, the floor is yours.
Thanks, Ellie. Good afternoon, everybody. I'm Lukas Morand from Fraunhofer Institute for Mechanics of Materials, and I'll give you some insights today about why data access management and utilization is relevant for material manufacturers. And I would like to start with an example today from textile manufacturing, which is one of our use cases in DiMAT. And I guess that this example will also fit to your organization. So in textile manufacturing, we have typically a production, and in the production, there are several processes that form a process chain. In textile manufacturing, this is spinning, weaving, knitting, finishing, and dyeing. And the material is typically inputted to such a process, processed, and then given to the next process, and then this forms this so-called process chain. In textile manufacturing, we have a fiber that gets processed to a yarn, to fabric, and then at the end to a textile. And the fiber, while getting processed, has different material states, or the material has different states during processing. And also, typically organizations have their own research and development department. They also take specimens from production, they process them, they do tests, and from the tests they get different data sets. So here we have already a bunch of different data from production, which can be sensor data, process parameters, and so on, and also data from research and development, which is testing data, and also different material states. But the research and development departments typically also do numerical simulation, which are on the next slide. Yes, thank you. And typically they do process simulations or material simulations to get the material properties. And here we get once more different data sets and much more information that we have to handle. And on top of each other, typically organizations have their external databases, which is on the next slide. And so they are connected to external databases. This means like information that you share with partners or that partners share with you, but could also material databases, norms, or could also be literature. And this is also one other bunch of different data that one has to handle. And you see, it's really a challenge to get an overview of this data and handle it. And the challenges I can quickly summarize are the heterogeneous data sources that we have. So in this textile manufacturing examples, we have already a lot of data sources like sensors, process parameters, testing data, simulation outcomes, simulation parameters, and external databases. And these data sources are often like in processing and sensor data. It could be time series, but it could be also field data like in numerical simulations or other metadata. As you can imagine, these heterogeneous data sources do have heterogeneous data formats, as said, time series, but also are like lists, but also field data and so on. So you cannot just take all this and store it into one database in a straightforward manner. And also, can be easily seen in this example. There are complex workflows, like data processing workflows. So it's not just that one has to store one data item and that's it. Data items are typically connected to other items because they get processed. So for example, you get data from the production, like this textile, which has a certain material state. This gets processed by the R&D department. They do a specimen. The specimens go into a testing machine. The testing machine gives you another data set. This data set typically is the source for numerical simulation, where you fit a simulation or material model to it, and then you get an outcome. And at the end of such a complex data processing workflow, typically you have a decision that you make at your organization. And you have to it's really challenging to get all this data, represent all this data as a one workflow. And this directly comes to the next challenge, which is data provenance. No, I'm not that far already. Which is data provenance, and that means that you really have to trace back all this information. So when you make a decision, then you need to know where this decision came from. Maybe if you do the decision today and you get asked why you have made it, then it's easy, but maybe this decision has been made like 2 or 3 months ago. And then you have to really trace back where your information came from that leads you to this decision. And then Let me quickly introduce also the FAIR principles of data that data management should adhere to, which is findability, accessibility, and interoperability, and reusability. And this is also very crucial to adhere to, so that you have a really good data management. Findability means, as easy as it may sound, that you can just find your data, which is also easy if you save something today. And I will ask you, but if you save something 2-3 years ago, then it's really can be really hard to find it. Accessibility means that if you have found it, you need to know how to access it. It could be easy with text files, but difficult with numerical simulation files. Interoperability just means that if you want to process your data, it should be very easy and you don't have to reformat the data to get it into format that you can process it. So in other words, if you have a data processing tool or want to apply machine learning, you should just plug it into your database and it should work. And last but not least, reusability. This is the overall aim, that you can really reuse your data also in many years. Also in many years in future. That means that every data that you save should be really good explained and described, and everybody should know what is the meaning behind your data. And now you can go to the next slide, Ellie. And here we come with the DiMAT Cloud Materials Database, a solution that we have developed in DiMAT, in short, CMDB. And the CMDB tries to overcome all these challenges. We have basically four basic functionalities. The first is data integration. That means independently of the data format and the source of data, you can integrate it into the CMDB. And while integration, it gets harmonized to a common format that everybody can work with. Also, while integration, the data is linked, so you can form these complex workflows and represent them in the CMDB. And we have data exploration capabilities, which mean that we provide some functionalities to discover all the data, like easy things that visualize the graph, but also search functionalities for getting out your data and explore the database. We also provide the option to generate new knowledge. This is what I meant with interoperability. So you can plug in new tools, scripts, simulation software, third-party software. You get information or data from the CMDB, you process them, store it back, and link it. So you get your workflow represented. And the overall aim of that is to derive recommendations from the data and make decisions. And we want to support a knowledge-based decision making. And the overall aim is to enable this, to automate this even with artificial intelligence. Now let's have a look a bit at how the CMDB looks like. Yeah, here we see the web front end of the CMDB, which is quite user-friendly and provides a seamless interaction with CMDB. You can see in the navigation bar on top, knowledge, where you can add new knowledge items like organizations, experts, data sets, and so on. In Explore, you can find the capabilities to explore and search the database, and tools will give you some tools to work with. On the next slide, we have a screenshot of the knowledge graph as it is at the moment in DiMAT. It's not very much populated, but it will get more populated, I hope. If you get a closer look, you can see, like, for example, the Fraunhofer IWM, which is registered as an organization. It's connected to experts. The experts is connected to material models. And you can also see the pilots. So that we have 4 pilots in DiMAT, which are the use cases. And the pilots are connected to their data sets. We can also see documents, devices, and processes and apps that have been registered in the CMDB and linked to each other in a meaningful way. Also, the CMDB comes with a Python interface, which is on the next slide, which can be used for automated data processing. I want to highlight the box on the left, which shows you that with only 2 lines of code and the DSMS SDK, which is a Python package that you have to install, with only these 2 lines of code and your credentials, you can already access CMDB, get data out there, plug in or use your scripts to process the data and save data back in a very efficient and easy way. And then you can derive plots or do work with scripts, as you can see on the right, but I don't want to go into detail there. I want to quickly summarize the CMDB. It is a robust data management tool for handling heterogeneous data in a fair manner. As we have seen, it provides you with a seamless data integration capabilities. We enhance data with enhanced data exploration capabilities. We support the generation of new knowledge with scripts or even third-party software. And we aim to support derive recommendations and support decision making. The CMDB comes with a user-friendly web interface, as you have seen, and also with a Python SDK for automated data processing. And what I have not said until now, but which is really also important, is how you use the CMDB. So the CMDB is not meant that you have to replace your existing database system. That would be really a lot of effort. The CMDB can run in parallel or on top of your database systems, actually. You can connect it to all your data sources or your databases, bring them together, and you can manage them with the CMDB interfaces.
All right. Thank you, Lucas, for this excellent and very informative presentation. And now we're moving to our second part, Semantics Matter, representing and analyzing industrial business processes with knowledge graphs. This is going to be presented by Kostas.
Yes, thank you, Eli. Hello, all. I'm Konstantinos Tsitseklis, and today we're going to talk about why it is very beneficial to represent the industrial business processes using knowledge graphs and why semantics matter. So, Eli, if we can go to the next screen. Yes, if you remember the example Lucas gave earlier on, we can have an organization active in the polymer industry. They do some textile production, and in order to produce some textiles, various steps of a process should be followed. When we go into further detail, though, inside the logic of each such process, let's say inside the logic of the spinning process, of the weaving, of the knitting, or any other one, more challenges arise. Because we need to decide on things like how this process is structured, which devices are used, which material should be used, and in which state should they be in, and many more such details. What we currently have in the industry is that many SMEs describe their data using their own terms in their own data formats, meaning that, let's say, for the polymer industry, we can have two companies, company A and company B, referring to the same thing, let's say the melt flow index, using two different terms. Also, they can store their data using vastly different formats. For example, an SME can use SQL databases, the other SME only Excel files, or even only text documents. This means that the structure of the processes is not reflected in their storage, and thus interdependencies become very difficult to detect. Also, the automation of processes becomes difficult, because if there is not a common vocabulary and a common way of storing the data, developing algorithms that automatically retrieve data from various parts of the business or between different businesses becomes very difficult. Also, when an SME hires personnel, this personnel needs to be acquainted with a specific terminology used inside the particular SME. So, all in all, unstructured knowledge hinders further data analysis. So, moving to the next slide, it's what we propose. We propose that to address all these challenges, we need to represent data in another format, using knowledge graphs. You can think of knowledge graphs as a kind of database, but very different from the traditional SQL databases. Knowledge graph representations are beneficial for the manufacturing processes because they can store a variety of data formats. They have different entities and relationships, and the entities represent various concepts used in manufacturing. Let's say they can represent materials, they can represent devices, they can represent properties of materials, and so on. And the relationships join these different entities, depicting the semantics behind their interdependency. thus making it easier to understand these dependencies among various data types, for example, materials, devices, equipment in general. Also, it increases data traceability, and it allows for connecting with advanced artificial intelligence and machine learning tools to support further analytics. Moreover, knowledge graphs can be easily modified in order to represent changes in the manufacturing processes. So, if a business process slightly changes, this can be more easily addressed with a knowledge graph than a traditional SQL database with table formats. In addition, knowledge graphs often support visualization tools that make inspection easier for the personnel of particular subgraphs that are of interest for each use case. Now, let's talk a little bit about the knowledge acquisition framework, which is the DiMAT knowledge graph, if we can say such a thing. What we have here for CAF is that it is a toolkit that aims to represent holistically the industrial business processes, focusing on two different viewpoints, focusing both on the manufacturing materials, their properties, their desired states, unwanted states that may cause security issues, their structure, but also focus on business processes and the recipes, meaning the order of operation. So, using a knowledge graph, we can describe a manufacturing business process by depicting how it is split into different steps, and for each step, which devices need to be configured and how this configuration should be set up, and which materials should be provided as input into which step. In order to make the toolkit interoperable, in collaboration with CMDB, CAF supports the common vocabulary for naming the elements and the instances of the elements, enhancing the toolkit's interoperability. The structure of CAF, which you can see in the right part of the screen, allows for the toolkit to be used across vastly different kinds of industrial business processes. So it can be used to represent a business process focusing on polymers. It can be used to represent a business process that produces glasses or batteries or any other manufacturing process in general, because it is a very adaptable knowledge graph schema that can support various different situations. Using CAF, the data are stored in a structured manner, and so the compliance with the fair data principles that Lukas explained earlier is ensured. Let's talk now a little bit about the supported features for KF. First of all, we provide an easy-to-use interface to the users for data exploration, one of the most important aspects of the toolkit, where with the use of many drop-downs and search fields, the users can search what is stored in the database and also understand the interdependencies behind different kinds of stored data types. For example, materials and devices, materials and their properties, and so on. Also, we allow users that know Cypher query language, it's the query language of Neo4j, to provide their own custom queries in order to retrieve more customized results. Moving on to the next slide. Another important aspect of the knowledge acquisition framework is the ability of the user to generate visualization of appropriate subgraphs. Using the knowledge graph structure, it is easy to visualize subgraphs that can be used in order for the user to easily understand parts of the business process and answer questions like what is required to produce a product, which materials, for example, or which devices are required for a particular step of the process. The user can either save these images in their device, or they can extract the information visualized in a table format if this is needed to support further data analysis, like the one seen in the left part of the screen. And moving to the last main functionality of KF is that it can be used also as an analytics endpoint. It can be used as a storage endpoint, as we saw earlier on, and the user can use it in order to discover what is stored there and how the different kinds of data depend on one another. But also it can be used in order to provide some analytics. The analytics that can be performed over a knowledge graph can be used to extract useful information that can help the business, the personnel in the business, in order to make decisions during the design phases of the manufacturing. We can support a variety of different knowledge graphs related algorithms, like similarity extraction between the different entities, community detection, link prediction, or so on. And out of the box, we support analytics based on the similarities, so the users can select, let's say, as we see in the right part of the screen, a material, and they can select to retrieve the most similar materials to it based on certain properties that can be customly chosen and weighted by the customer. The ability to also develop more tailor-made approaches for the KF is also supported to suit more advanced needs. And wrapping it all up, what we see is that nowadays SMEs use their own terms, their own data formats. Sometimes this is outdated, and in most cases, it is unstructured. This hinders the analysis of the data and makes their exploration more difficult, and also hinders the further data analysis that can be used in order to obtain useful insights. Using KF, we provide a structured means of storing the data and analyzing it by relying on a knowledge graph flexible scheme that can be used, as we saw, in various different domains. KF supports the developed DiMAT vocabulary, which is done during the scope of the project, and it can be used in order to be connected with other toolkits and act as an information retrieval point. Those of you that are more interested in how KF works can either choose to see a YouTube demo video. It's the first release of the toolkit, or they can read our publication detailing more the different aspects of KF and how it can be used in order to be connected with another toolkit of DiMAT, the Digital Twins Process Control. So thank you all very much.
Thank you, Kostas. Now we're moving to our final part of today's presentation, LCA for non-specialists. This is going to be presented by Thanasis.
So hello everyone, I'm Thanasis Karagounis from DRAXIS Environmental, and I'm going to present you about the life cycle assessments and why this is important. And as it is for non-specialists, I will try to keep it simple to get the basics out of it. And yes, so in the context, of course, of the DiMAT project, LCA basically is integrated in the Make LCA toolkit. It's the materials, environmental, and cost life cycle assessment toolkit. It's a part of the DiMAT data and assessment suite, one of the three. And so it allows users to visualize the results, the core results of having a life cycle assessment and also a life cycle costing. But before further details about the toolkit, we must first understand what is an LCA and what is an LCC, and then understand why are those important. To the next slide. Yes, so the LCA methodology, nowadays it's a well-known methodology. It follows LCA principles based on certain ISO standards. And what is it about? As some of us know, it's assessing the environmental impacts of either a product, either a process or a whole project throughout its life cycle. And it consists of four main steps. First is a goal and scope definition. Then it's inventory analysis. The third part is the impact assessment. And the final is the interpretation of results. And I'm going to give a few details for each one in the next few slides. So regarding the goal and scope, first you must, as you may understand, that you must set the reason why you are doing your analysis. What is your goal? So based on that, you have you must set the boundaries of your system under study and set the right functional unit. Regarding the systems, the boundaries of the system, in an LCA study, we have various approaches. I'm just giving you the two main approaches, the cradle to gate and the cradle to grave. So for example, in an industrial an industrial study of an LCA, if you want to understand what are the main environmental impacts of producing, for example, plastic, for example, you should involve the processes from the very raw material extraction till the point that your product is ready. Now, this is the cradle to gate, as we say, but if you want to have a more whole assessment, you can expand the boundaries. You can you can go to the cradle to grave, mainly adding the usage of your product, and of course the end of life, the treatment of the waste after the usage. And of course, as I say, you must set a good functional unit that it's a reference to collect the data and to present after calculating your impact. It's very crucial for fair comparisons. For example, you should, regarding data, for example, a good functional unit would be compared, for example, energy consumption per 1 kilo of your product. Of course, it's not only about mass, it could be time, it could be energy, it could be other units, but let us not complicate things at this moment. So going to the next step, it's about the inventory analysis. So this is a part which one should collect all the necessary data based on the system that one sets. For example, you can see here all the stages, which of course involve processes under sub-processes. Of course, you understand, for example, that in an industry, here we would include all the processes producing your product. And to have a full inventory, you must acquire all the inputs and outputs, meaning that you need to have the raw data of the raw materials used, the energy used, and all the outputs, meaning of all these processes involved, what are the waste produced, what are the emissions to air, soil, or water, causing eventually, let's go to the next slide. Of course, all these emissions, as we call it in LCA terms, flows, all these emissions basically will be translated into environmental impacts. And I'm giving a well-known example. You can understand that if a process emits greenhouse gases, a good amount, let me say, of greenhouse gases like carbon dioxide or methane, this will eventually have an impact of global warming. Or if, for example, if there's an industry producing fertilizers, we would need some specific mineral resources that would cause the impact of the respective depletion of resources. And of course, the last step would be to interpret all these results, but this is not something that we need to see right now. Also, moving on to the LCC, the cost life cycle assessment. This is also something involved in the MEC-LCA tool. So just a few words, I don't want to go deep in this. So this is also a methodology based on the specific ISO standards +1 ISO. It's a methodology mainly calculating all the related costs of a product, process, or project during its whole life cycle, according to what you want to study exactly. And it's most of the times used alongside an environmental LCA. You can see some, you can be using this for for your company or industry, for budgeting, for comparing technologies, and all this to supporting your decisions related to costs. And you can see 6 main categories of costs that this involves. For example, we can start with initial and installation costs. There are then the operational costs and the maintenance costs. And finally, you can see the support costs and disposal costs. So moving on. Now, focusing more on the tool, the MEC-LCA, let me clarify, it's not actually calculates all this, the LCA and the LCC. This is something that needs to be done externally out of the toolkit because there are several softwares that need to be used in order to all this data to be translated into environmental and economic impacts. So after doing all this analysis, those results are imported into the MEC-LCA toolkit. So the toolkit actually focuses on the final users so that they can extract value from these results by using a very easy and interactive dashboards which have an informative character. And so some of the main benefits of having all this knowledge provided to you after the analysis would be for the value chain that one would like to see to inform, to get the information, would be to examine what environmental and impacts would be from using various materials, energy consumption of several processes, and of course, one might wants to compare different scenarios based on that. So it would be a very nice opportunity by using the toolkit to examine these different scenarios and support their design, support generally decisions. Next one, please. So this is something, an example, let me say, by using the toolkit, one could see by choosing one specific impact here. I'm just showing you, for instance, climate change. For example, we can see the scenario, the first scenario. It has many processes involved in the value chain, and they can see how this how each process actually contributes to climate change impact, and having the insight, have the information of what contributes more. And of course, you can compare different scenarios. For example, regarding the green bar, one specific process, by having something alter, maybe a technology, maybe an energy source, you can see how it could be less. So having seen all this information could support their decisions. And the next one, please. Also, it's more interactive for you, getting the knowledge. You can see to the right hand. One can understand by having their input on how much is their energy consumption, their kilowatt hours, for example, changing this number, how this would influence different impacts. For example, again, here I'm showing you the carbon footprint, and also by changing the source of electricity, how this would impact, for example, by changing natural gas to wind turbines or oil, etc. And to the left, of course, there are also some depictions of the costs throughout the stages and understand their economics. So to wrap it up and give you a conclusion, the Make LCA toolkit, by having all these visualizations through LCA, from LCA and LCC analysis and results, can contribute actually to one SME, to the industries companies which would like to use it to reduce their environmental impact through all this analysis that one has and stay compliant also to environmental laws. The LCC could also provide them to plan for their costs throughout their life cycle, to balance their sustainability levels with the cost effectiveness, and of course, at the same time, stay competitive. So that would be from my side. Thank you all for listening to me.
Thank you, Thanasis, and thank you all. The time for our session today has passed. Thank you all for tuning in. Please join next week, where we're going to be speaking about material modeling and material prediction. Again, a very short 40-minute, easily digestible session where you'll get to learn all those important things regarding material manufacturing and how digital solutions can support your business and operational processes further. Thank you all, and I wish you a good day. Bye.